Hello, deep learners. It is good to see you. I'm Sophia Vikland, and our special guest tonight is Herman Ross, the head of CARLA. Herman will talk about training autonomous vehicles to drive from the comfort of your own home with CARLA. Herman, welcome. It is great to have you. Could you please say a few words before we start?
Sure. Yeah, definitely. So basically, I worked for a while, like during my PhD in the field of simulation for autonomous systems. We did a lot of um, novel stuff, including simulation for autonomous driving. We with the SYNTHIA project, which was one of the first big projects that really kind of like started this idea that we could do more in terms of simulation could do more for autonomous driving that what it was doing until then. We could use simulation for training autonomous driving models, not just verification but also training. Somehow that was the spark that then led us to CARLA. So after this big project, Cynthia, we decided to um, basically trying to come up with something that was fully open source and basically trying to democratize the field a little bit because we saw that those tools were expensive. Those tools were hard to obtain, hard to create, and people were reinventing the wheel. So I started that project while I was still at Toyota Research. So I was taking care of a few things at Toyota. So on one hand, I was working on autonomous driving from the perception and machine learning side. At the same time, I was also trying to create the tools that we could use internally to verify and to prototype new algorithms. And that was kind of like the internal simulation platform that we're using at Toyota. Um, it kind of like everything kind of fall together. We realized that it was hard to be creating new simulation tools every time, and we believed that we could do a lot of good if somehow we could put together an open source splitter, and that was the arena of CARLA. So we did that in collaboration with Barcelona and Intel. So at some point, Toyota became a sponsor. Actually, I moved to Intel, and once at Intel, I just kind of like started working as a program manager for simulation. So kind of like taking care of the CARLA organization, making sure that the project keep progressing, moving forward, align the agenda with our stakeholders, so which are basically the community, OEMs, government, researchers, and so on. Yeah, that's a little bit the story, and I keep working in the field of simulation, autonomous driving, perception, planning, related topics.
Great. Can you hear me okay?
Yeah.
Okay, so Herman, let's start our presentation. I'm going to make you a host, and you could, do you want to talk or do you want to present some slides?
I'm going to present some slides. I'm going to present many slides, actually.
Okay.
Hopefully it will be entertaining. So I have titled the presentation Training Autonomous Vehicles to Drive from the Comfort of Home. So this is very aligned with the current situation we're all living. So I hope this is an entertaining talk. Basically, I would like to show us, talk a little bit about the current state of autonomous driving and different approaches that are out there to actually have vehicles driving around based on data. So collecting and training models from data, and how we can use simulation to do this, or what's the role that simulation can play today and also in the future. So this is basically what everyone expects to see when we talk about autonomous driving, right? So this is a footage from Intel Mobileye. So here you can see a trajectory in Israel where people get into the car, which is driving fully autonomously. On the top, left, you can see a visual representation of what the car is seeing right now. So pedestrians, parked vehicles, and so on. You see these gray and bluish arrows, which is basically the planner trying to decide what to do in real time, like when to stop, when to overtake another vehicle, etc. As you can see in this video, things are going pretty well. So we could consider this sort of a scenario a success. So no one died, right? And the vehicle didn't crash. And they managed to go fully autonomously without any human intervention for around 40 minutes, 45 minutes. You can see how the vehicle has to approach different challenges, including merging lanes when the traffic is getting heavier, responding to traffic lights, etc. I think there is some message. Oh, okay, sorry. Okay, so basically it works pretty well. So we can see that the vehicle is detecting everything that is important in the scene, including pedestrians, the position of other vehicles. It's doing a pretty good job. So then why are we here today? Well, the problem is like this is not always the case, right? Sometimes systems can't cope with the real world so well. We know this, we have seen this in the news over and over again, where basically systems end up having problems and causing accidents and crashes, sometimes caused by the autonomous vehicle itself, sometimes caused by the world, and the autonomous vehicle wasn't able to react to the world. So here there are two good examples. One on the left, the Tesla crash, which was caused by the Tesla, one right, one of the accident by Uber, which wasn't caused by Uber. It was actually caused by another vehicle, but ended up affecting the Uber. So the Uber vehicle, the autonomous vehicle, wasn't able to react and to cope with that situation. So definitely, autonomous driving systems are far from perfect. Well, the reality is like if we check the different levels of automation from 0 to 5, from no automation to full automation, getting to level 4, moving from level 3 to level 4, when we have high automation, or in other words, something that works all the time, as long as we keep ourselves in the, let's say, verified operational domains. For example, let's say certain type of highways or certain parts of a urban environment, like a city. Getting there to that level 4 is very, very complicated. So coming up with warranties like this system is going to work all the time as long as we keep inside this ODD, operational design domain. Even that might sound kind of like a protected environment. Well, this is still a challenge. It's still a very important challenge. In order to get some context, so here, so I have brought the official data that companies in California have to report to DMV. So this has been released this year and refers to the end of 2019, beginning of 2020. So here we have a plot with the number of testing vehicles for each of the companies in the area. So you can see on the left how Cruise and Waymo have a nice fleet with hundreds of vehicles, and they are running tests pretty much every day, non-stop. So you could expect that these companies are making a lot of progress, which is true indeed, but still the problem is very complicated. You can see how complicated the problem is if we take a look into the disengagement. So basically, one simple metric is how many times a safety driver will have to intervene per number of driven miles. Ideally, what you would like to see here is that the The miles until disengagement, the light blue bar is as high as the dark blue bar. So you will see, you would like to see infinite number of driven miles and an infinite number of miles until disengagement. So no disengagement, everything is light blue, everything is amazing. Notice that the vertical axis is actually a logarithmic scale. Um, so the difference between miles under disengagement and the actual number of miles driven is very, there's a big gap for everybody. So even the one uh, doing their best uh, are really far from solving the problem. Another issue with this data, these reports are voluntary. So basically, they are not calibrated. So when we see Baidu, Waymo, and Cruise on the top, basically with better miles entered disengagement metrics or better results, we have to take this all carefully, because different vendors, different OEMs, startups are reporting results in different conditions. So they are actually driving in different areas. They're using different protocols to basically have a safety driver triggering a disengagement. So it's not straightforward to compare between different companies. This is just here to give us basically an overall understanding of where do we stand today. And you can see that there's still a lot of work to do. Um, the thing is, like, it's a very complex problem. So traditionally in robotics, people have tried to approach navigation problems using a divide and conquer approach. So that means we're going to have a platform. We're going to try to work on a decomposition of the big problems into subtasks. So we're going to have sensors, and then those sensors input is going to be collected and analyzed by a perception stack. That perception stack is going to have modules for different problems like object detection, semantic segmentation, depth estimation, optical flow, forecasting of object motions, etc. Then maybe we're going to have a planner that is going to ingest all this information, or we're going to have a sensor fusion module, and then all this information is going to be merged, and the output of that will go into a planner, and the plan will go into a controller, and so on. So in the end, you will end up with something like the diagram on the right, where you have a bunch of sensors, you have different tasks for data management, different tasks for perception, different tasks for planning and work modeling, tasks for behavior generation and control. So this means that you need to manage to do all of this well. If something fails, even if you have safeguards, even if you have a backup, chances are that things will get screwed. They will get broken easy. In a sense, you could argue that we're making the problem perhaps more complicated. So we need to carefully discuss if this is the right way to go, what are the shortcomings of these sort of approaches. But this traditionally has been the way to go, right? So we have a rich platform full of sensors. We have different teams working on different parts, hardware, perception, planning, and hopefully at some point we manage to put a system together. The problem with this is like, okay, you have your system, you have your perception stack, you have your planner. Can you cope with extreme cases? Can you, how does your system, how do the different modules cope with extreme cases? And here in this slide, you have a list of extreme cases, like starting from the top left, you see a duck or a goose crossing the road. Probably the engineers working on the perception stack, whether detection or semantic segmentation, didn't think too much about about what to do when a goose is crossing. It's definitely something you're not gonna find very often. It's one of those weird corner cases. Well, now you have seen it. Now you have to start collecting data. You have to start trying to find a way to take care of that, whether with your detector or with your semantic segmentation algorithm or anything else. Yeah, other extreme cases like in this intersection, the crazy amount of traffic lights, like which one is your light? So if you're trying to make a left turn, which one should you be? Definitely, this is not a traditional configuration. If you are a vehicle, if you are a driver in cities, probably even if you don't know exactly which one is yours, which traffic light is assigned to you and you have to respond to, you will still be able to do some reasonable choice. You will be cautious in the crossing, but you will probably be able to go through the intersection. Um, an autonomous vehicle, which depends on traffic light detector, will probably have troubles here. And so all this information needs to be pre-baked into a map, into a density map. Someone needs to bring like the understanding, the knowledge of which traffic light is the right one for the vehicles in an offline state. Otherwise, this becomes just pretty much impossible for the current technology. Yeah, so if we continue with exceptions, you see even simple stuff like stop signs. So this is actually a frame that I borrowed from Andrea Carpathy, senior director at Tesla. Um, he he was presenting this case, which kind of like illustrates very well the point. Like stop signs, something as trivial if you want. Uh, it's actually a very complicated task. They can be different locations, they can be occluded, they can have like text underneath telling you when to disobey the stop or in which conditions the stop apply. And so there's such an incredibly large amount of variability that you will need to be readapting and retraining your detection algorithm uh, every single day. And then if we move past perception, there's still the thing of, okay, what's the right policy? What's the right thing to do here? What should I? How do I move forward? So here in the bottom, I have brought like a few complex cases. So what to do in this sort of situations where traffic is crazy? You really need to be aggressive to push your way through. Can a policy define the way we define them today, cope with these cases? Uh, how is the policy going to react if it gets conflicting signal from any of the perception modules? So I think we should be considering all these problems. Now, in recent years, there has been an alternative current or school of thoughts that has defended behavior cloning or imitation learning as an alternative approach. I'm going to talk a little bit about the potential of behavior cloning and why it could somehow enabling new solutions for these complex cases. So for if any of you is not familiar with behavioral cloning, the idea is not new. The idea was introduced back in the 80s by Bommerlew and others, and then LeCun kept working on that at the beginning of the century, and later we have seen a lot of progress done by Rosdahl, by Felipe Codevilla and colleagues, and many others. The idea is simple. The idea is to actually, instead of trying to build everything as a set of modules that have to talk to each other and try to hard code a set of rules, we try to learn them from human demonstration or from demonstration. Let's say we assume an oracle. We could say that A human could be a good oracle for driving in most of the cases. And we collect data about how the human acts, how the human makes decisions. For example, we can assume that the output space to control our vehicle is basically the angle of the steering wheel and the throttle. We can collect this data. So we can try to correlate a set of inputs, for example, images coming from cameras, and a set of outputs. We can use that information probably along with other auxiliary information like speed or anything else you have handy to train a neural network or any other machine learning classifier. This is typically called behavior cloning. One of the restrictions, one of the limitations, that you need demonstration. Someone needs to demonstrate. Someone needs to be the oracle. This idea actually got people very excited at first, but then they found that hard to scale up. And I would like to talk about why in a few minutes, and what have been the solutions proposed since then in order to scale it up and try to produce systems that actually kind of work. Well, one of the advantages of this idea is that you are not really dealing with shortcomings or limitations of the different perception modules. Basically, this module, the neural network, is just dedicated to drive, to navigate around. So even if you haven't been able to fully solve the problem of object detection or semantic segmentation or any others, this network is able to go with data and produce a control output. So we haven't solved any of the actually very complex computer vision problems, but still we are able to navigate. The other way around is actually not true. So even if we solve several hard computer vision problems as we know them today, for example, object detection, we have no warranties that we'll end up being able to drive correctly. So that's actually up to our policy. So this technique is kind of following on the policy, on creating the policy that is able to navigate directly from data. And there are many variations that I'm going to be talking about that makes this a bit more tractable. As you can see here, one of the first complaints that you could highlight here is like, maybe it doesn't make too much sense to move from an input representation based on images directly to an output representation based on control commands, and that there are many things, many knowledge that we already have, and we can actually inject into the system, both about perception and representations that are good for perception, and also about representations that are good for control. So this is a work that was presented back in 2016 by NVIDIA, where they use this technique with one camera. They use 3 cameras for collecting data, but just one camera for actual navigation. They managed to train this neural network and basically deploy it in this Lincoln MKC to drive around New Jersey. This was basically a continuation of an old work done by LeCun and others, but it's scaled up and using new technologies like the Drive PX and all the new data acquisition and deep learning frameworks that we have today. Results were relatively good. Some of the limitations of this technique is that it's actually just following the lane. So it doesn't have any plan. It's just reacting. It's a reactive system, which basically is making decisions on the fly without proper plan. But the system itself was simple enough. As you know, it was based on a very compact neural network, few convolution layers. Uh, Data acquisition was relatively straightforward. Uh, and yeah, they managed to make it work. So it's by itself was a nice, a nice contribution. Um, Now, the system itself, let me give you a few details. So the part that becomes a bit complicated here is actually the data acquisition. Um, in order to scale the system up and to make it really generalize and cope with all different kind of environments, uh, you need a lot of data, and you need to be very careful with the way you collect your data. You really need to bring good representatives for all those different environments and all those different situations. For example, traffic intersections with lights, without lights, unprotected left turns, different type of curvature, etc. So this is very data hungry. So in a way, you could think that, well, this is a huge limitation and this technology will not be able to take off. However, this is in part due to the input representation and the output representation that they were using in the work. So they are using a very, very, very small neural network to really take care of the image processing and the decision making. So you could argue that if you could add different levels of abstraction to the system and abstract some of the information away, creating an input representation that is more abstract, the neural network might do a much better generalization job. That's basically what I want to show in the next slides. But here, coming back to the data problem, so one of the problems that they observed, like making the network react was requiring them to actually synthesize novel views. So the reason why they have 3 cameras in the system is not that they use them in runtime, it's for data collection. So based on the 3 views, they can synthesize new viewpoints that then they can associate with the commands that they recorded from the driver, so that in a way they can ask the neural network, because the driver is obviously always driving in a nice way, but you also need to present examples where actually the driver has to recover from, let's say, a wrong position. When the car is actually not in the right place, how would the driver recover? So basically what they are able to do is they can generate an image that looks like if the vehicle was shifted from the center of the lane. They will be able to provide basically the ground truth for that. And that sort of is critical for the network to learn what to do in those situations where you really need to react. Something is not working as expected. You need to compensate and come back to the center of the lane. This is in a way one of the limitations of the system. Like the data acquisition becomes a bit more complicated. You need to play with this trick of the 3 cameras to sense the new views. You need to generate a lot of intermediate data to pull this off. So it's nice, but it has some limitations. Then a colleague of mine, a student, Felipe Godevilla. So basically the story is simple. I actually saw NVIDIA's paper, and I actually visited them. I had a ride in the car and say, okay, this is great, but why is this just following the rule? Why does this thing doesn't have a plan? And I proposed to Felipe Godevilla to basically work on changing that. We basically turn what is called behavior cloning or imitation learning into conditional imitation learning. The idea here was basically to provide a plan to the system to follow. Same thing that you do when you drive your car and ask Google Maps to tell you where to go. So how to get there, when to turn left, when to turn right, and so on. So same idea. And some of the advantages of that is that now we can actually tell the car where to go, but also Felipe came out with a way to simplify the data acquisition pipeline. The idea is actually very, very interesting. By the way, you have the source code of this project in this URL. So everything's in GitHub. So if you're interested in knowing more, feel free to go there and play with the code. But yeah, as I was mentioning, the idea behind conditional limitation learning is that we are gonna add a set of plans. We are gonna add a plan that is divided into a set of commands. In our case, the commands were straight, left, right, and nothing. So basically, when you approach an intersection, you have to typically to make a decision if you're gonna go left to the right, keep it straight, or if you are at a different location, probably you just have to keep following the lane. So that's the nothing part. So the architecture looks like this. You have the same neural network that is in charge of taking input images and other information, like in this case, speed. And it's also going to take a plan that comes from the global planner. So that plan is going to be a set of commands that are going to be given when we approach a place that has multiple possibilities, like an intersection. And the network is going to process all that information and it's going to produce as an output steering command and throttle. So kind of the same thing, but now we have a plan in the middle. Architecture itself, just a small variation of the previous architecture that you saw at the in the NVIDIA paper. So here we have a convolutional neural network processing the image, then other type of measurement like a speed go through some NLP. They get combined. For the conditional part, actually, something that Felipe did that was very interesting is to have multiple heads, like multiple branches. One head of the network specialized on going straight, one head is specialized on turning left, one head is specialized turning right, etc. Based on the command that is provided by the planner, they just select the right head that is specialized in that action. So that head knows how to do very well that kind of actions. It turns out that this is one of the simple and fast ways of training a model like this. Also, they decided to simplify, in a way, the data acquisition pipeline. Instead of requiring multiple cameras to synthesize novel views, they decided that it was just easier to inject noise. So when you are driving, you actually inject different levels of noise. If you're driving, it's like imagine you have someone really like messing with you, messing with your steering wheel, or messing with your shuttle. You have to kind of like compensate for that. You have to recuperate from that state. One of the limitations that these systems, this approach introduces, like this is not really safe to do in the real world. Like, you probably don't want your system to be injecting noise to your vehicle in the real world. So all this approach and some of the approaches that we'll be presenting have been trained in simulation. So in autonomous driving simulator called CARLA. These are some of the setups that they did for experiments. So you have like two towns, one that is used for training with a certain layout, and another town that is used for testing. The idea is to see if training in the training town, you can generalize and get good scores for the testing town, where the task is basically drive from point A to point B without making any traffic infractions. So that means not colliding with pedestrians, not hitting cars, hopefully not running traffic lights, etc. Here we can see some results. So this is a vehicle trained use conditional limitation learning. This is in the testing town. So you see that it was It's not really respecting traffic lights. I have a problem with traffic lights, but it's sort of being careful enough with other elements like vehicles, like pedestrians, and so on. So okay, not the best solution ever, but it was working relatively fine. So it was one of the first results for driving using conditional imitation learning. So I think we will give it a passing score. After that, on top of conditional imitation learning, Sauer et al. Back in 2018 proposed an improvement of the system called conditional affordance learning. And the idea is simple. Instead of having a neural network that takes a video input and a plan and produces as an output like the control commands, instead, the output of the network is going to be a set of affordances. And these affordances are basically a description of the ego vehicle, the vehicle that we're controlling with respect to the scene, like with respect to other vehicles that are nearby, with respect to the layout, like what's the distance, what's the angle of the vehicle with respect to the road, what's the distance to the center lane, have we seen a red light, etc. So a different output representation for the neural network. Then this output representation is ingested by a controller. You can imagine here a PID or an NPC to finally produce the control commands of throttle, brake, and steering. What Sauer et al. Show is that this approach produces much better results than just traditional conditional imitation learning trained end-to-end. The architecture itself is not that different. So as usual, you have a CNN for feature extraction, and then they are keeping memory from previous time instance, which is typically useful. As before, they are playing the conditional trick, where basically they have multiple heads specialized on the different outputs, like left, right, and so on. In this case, instead, they do that for affordances, and the final affordances are ingested by the controller to come up with a longitudinal control plan, a lateral control plan. And that's it. So here you can see a few of these affordances represented in a graphical way. So for the vehicle, you see the angle with respect of the lane. You see speed signs, the state of traffic lights. So all this information is kind of like collected into a bag of affordances and then passed to the controller to make decisions. This is how the approach works in CARLA. So here they are just explaining the technique. Let me just take you to the beautiful results. A few things to notice here. So this approach is able to deal with traffic lights, which the previous approach, conditional imitation learning by its own, wasn't able to deal with that. It's much better at basically keeping enough gap with the vehicle ahead, so it feels much more safe. And overall, the behavior is just much better. The reason behind this is that actually training something end to end, like from a high dimensional space like images to a very low dimensional space like control commands, just produces a very huge combinatorial explosion. It requires just too much data. It's very hard really to make the system generalize. If you are more careful in the selection of your input space and your output space, you can typically generalize much better. So this is something that is implemented in this project, and many people learn from this. And then people kept improving upon that. Some of the most recent works, in this case by Chen and colleagues in 2019, this learning by cheating was an amazing demonstration of the things that you can do if you have a simulator. The approach is as follows. First, they create an agent, a policy based on privileged information. In this case, privileged information means any information that can be provided by a simulator, but that you typically won't have during test time, something that you have during training. In this context, they created this abstract representation of the world where the agent gets the full picture of the road, the dimensions of the different lanes, the width of the lanes, where are the traffic lights, the state of the traffic lights, if it's red, green, the orientation, the speed of other vehicles. So basically, it gets the full picture of everything. So as if you had the perfect, the ideal perception stack, right? So what they do is that they train a neural network to produce control commands for steering and throttle based on this input on a simulator. And then they attempt and achieve actually to train a second neural network to imitate the first neural network. They call the first neural network privileged agent because it has been trained with privileged information, and they call the second neural network expert. So the expert's mission is to learn from the privileged agent. The privileged agent is cheating, has access to privileged information. The expert system only has access to like sensor data, like video feed, etc. Something that they show in the paper is that this approach, given access, having this intermediate step where you give access to your agent to this privileged information, first makes that agent to converge very fast and find very good solutions. And then it's very easy to train the expert to match the output of the privileged agent. So we know how to do that. So we are good at that. We are better to navigate the perception space once we know how the policy should behave. And it works. This is currently basically state of the art in driving. So let me show you some results. This is a bit of idea. So step one, you have this privileged agent, which is the one cheating because it has access to this privileged information. You train it to produce a nice policy controlling the throttle, the brake, and the steering wheel. And then you have the second step, which is, as I mentioned, a regular agent, which will try to learn from the supervision of the privileged agent. So the main advantage is that generalization is much better, right? So you get to better solutions that work better in test scenes that you haven't seen before with fewer iterations. So sometimes it's hard to discover a good solution. It takes just too many iterations, especially when you have a system that needs to react in a simulator in the real world. Finding good solution for those takes a lot of time. It's quite tricky. So in this case, with this approach, they managed to find these solutions much faster. So they got a better sampling complexity in terms of how much data you need to get to those results. Yeah, so basically, if we check the results on some of the standard benchmark on CARLA, so their approach that is called LDC managed to get 100% success rate in the different tests for different weather conditions and towns. On a much more complex benchmark, the no crash benchmark, where basically you need to not crash with anything, they managed to do quite well as well. Overall, better than previous approaches. And here you can see a little bit of how this agent drives. Okay. Yeah, and if you are interested in numbers, well, you can see how the different variation of LBC really did an amazing job in comparison to the previous state of the art. These numbers were very, very surprising at the time. Like I was, and personally, we created this benchmark. We were not expecting to see these numbers yet. We thought it would take a few more years to get there. But well, sometimes it's good to be wrong. Now, as you probably noticed, some of what these techniques have in common is that they actually require to use a simulation environment, a simulation for autonomous driving in order to train the systems safely. And all of them actually use the same simulation environment, CARLA. I'm gonna give you a quick introduction to what CARLA is in case you don't know about it yet. And if you know about it, I hope this is not too boring for you. So this is what CARLA looks like. And in a nutshell, we could say that CARLA is an open source project that gives you an API for simulation, right? So it's supposed to be flexible, supposed to be easy to extend. You can use it for research, development, and validation of autonomous vehicles. So it's basically there to help you with all the tasks. Sensor placement, if you have any experiments where you need to identify what's the right way to place sensors, or if you have to do A/B testing with different perception algorithms, or if you need to generate data and ground truth to train those perception algorithms, CARLA is there for you. Also for planning, you can train policies, you can evaluate policies. We provide a lot of interesting tools like the generation of background traffic. You can generate different behaviors for pedestrians, for vehicles, etc. We also provide you with a lot of tools for bringing your own maps, for designing those maps, designing traffic situations, etc. So overall, it's a very complete tool for autonomous driving simulation, and it has the main advantage of being totally free. CARLA is an open source project and is built around a community of users, which at the time is actually quite healthy, if you ask me. We have academic users, we have OEMs, we have startups, we have governments using CARLA, etc. So overall, we have a bit of a blend. People overall seem to be happy with the approach. Of course, people always want new features. We keep track of let's say, the popularity of CARLA or how well CARLA is doing through GitHub, basically using the Stargazer. So we have recently reached 5,000 stars. We kind of had like a linear growth. Itself, CARLA follows, as any open source project, typically follows a very complex structure. So we have the Open Source Research Foundation and the Computer Vision Center in Barcelona hosting the CARLA teams. Then we have sponsors supporting the development, like General Motors, Toyota Research Institute, Intel, KPIT. And then we have a nice ecosystem of partners and colleagues. So MathWorks, Alpha Drive, the Oak Ridge National Laboratory. These are entities very close to the development of CARLA, entities that are actually developing things in alignment with CARLA. We typically have a very tight alignment in the things that we're going to be releasing. Try to come up with a set of additional tools that work well with CARLA for our users. Also, here you can see a list of projects, both academic and from industry, that are using CARLA for different things, building stuff on top of CARLA, new simulators or autonomous driving stack, etc. From a technical perspective, so one of the most important things to highlight is that CARLA follows a very modular approach. So you have a server and you have multiple clients. You can connect servers and clients through two APIs, the C++ API and the Python API. And the idea is that the server will take care of certain aspects of the simulation, like, for example, sensor simulation and physics updates. And then client code will take care of many other things. For example, creating weather profiles, the traffic management, behaviors of pedestrians, and also if you are driving an autonomous vehicle stack to be tested in a simulator, your code will be in client side. So that's the idea. The idea is to be able to generalize as much as possible and scale up and out this simulation platform through multiple clients that can be distributed across a network. So an example, simple example of the API, both in Python and C++, we use the concept of blueprint, which is kind of like a class. You can instantiate different blueprints with different properties, like vehicles with different properties. Set them in autopilot, so they will start navigating, or you can give them a specific set of commands. Well, overall, this is just to reflect how simple it is to use the API. One of the most important parts, or something that we take very seriously, is actually sensor simulation. So sensor simulation for autonomous driving is one of the critical parts of the story. So we have to be good at simulating cameras and the different physical properties of cameras, also LiDARs, radar simulation, which is highly complex, other sensors like IMUs, GNSS, and even new sensors like DVS, and so on. So here we have multiple lines of work approaching these problems. We have from placeholder sensors that are just trying to produce a basic signal, sort of like a placeholder for the sensor. And we also have things that are more complicated, that really try to simulate how the sensor works from a physical perspective, trying to simulate how the electromagnetic wave propagates around the environment and bounces back, and so on. So we try to approach the problem from different angles, assuming different constraints. So some of the modules for real-time purposes, some of the modules dedicated to very realistic sensor simulation. And in addition to that, we also offer what we call ground truth. So basically, if you are training machine learning models or AI models, we offer you ground truth for pretty much everything. So privileged information about your scene, how the different things, the different actors are behaving, and so on. So this is just a quick demo of how CARLA can support the generation of multiple high definition video stream in real time. This is one of the most recent features. Here I show a little bit different ways to play with the physical parameters of your camera. So chromatic aberration, we can control the chromatic aberration, lens distortion. So if you pay attention to the edges of the image, you'll see that it's distorted. And so CARLA gives you the power to play with all the different parameters that you will find in a regular camera. And since not everything is based on cameras, especially in the field of autonomous driving, here we also show one of our recent updates of the LiDAR sensor generation. So you can play with different noise models. You can plug the noise model that matches your sensor. You will get data like this. Also, in CARLA, you can play with the environment, so you have full control of everything through the API. So you can decide to change the position of the sun, or make it cloudy, night, play with the lights of buildings or the lights of vehicles, make it rain, play with the wetness of the ground, etc. So basically, the API gives you full control of everything. An interesting aspect of the project is that we offer a lot of free content, so including 9 maps. So we have 9 public maps that we created for the community. We keep 2 maps secret for a challenge. We have a running autonomous driving challenge called the CARLA Challenge. We keep those maps secret, just to prevent people from overfitting to them. But yeah, we give maps for urban environments, highways, rural areas. We also give you the tools to create your own maps. And also our assets. So all the assets that we have created in these last 3 years, so vehicles, buildings, you name it, are also open source for free to you to take for commercial and non-commercial purposes. CARLA has the advantage of not being a black box. So it's an open box that you can connect to other tools, to other simulators. So you can connect it to popular simulators like Sumo or PTV Sim to do co-simulation. So you can decide that you have very nice scripts in Sumo already to do larger scale traffic simulation. No problem. You can actually connect Sumo API to CARLA. And as you can see here, they will be connected as a code simulator. You will be able to have Sumo driving CARLA, or CARLA driving Sumo, or PTV driving CARLA, or Sumo, or vice versa. So basically, the sky is the limit. So you have full interoperation between tools. Continue with kind of like creating situations and traffic scenarios. We also provide an engine that we created from scratch called Scenario Runner. that basically let the user to generate all the different traffic situation as a set of choreographies. So for example, this situation where we're in the black car and suddenly the Tesla just plops and we have to suddenly brake to avoid collision. So this is something that you can orchestrate easily using a scenario runner. We also offer tools to process and create your maps fully procedurally from standards like OpenDrive. Fully automatically. So you just have to pass your OpenDrive file and we'll convert it to a CARLA map for you. So you have an OpenDrive from your area, you can quickly bring it into CARLA. And a recent improvement of this, we now also support OpenStreetMap. So you can go to OpenStreetMap, you can select a region, you download that region, we can import it and create a map totally procedurally in a few seconds. This feature, so we rolled it out a few days ago. So basically what you get is a map that allows for traffic simulation, but still you don't get all the nice environment decoration. So you don't get the trees, you don't get the other buildings yet. So this is something that we'll bring in future versions. Yeah, we also have a connectivity with other autonomous driving stacks like Autoware stack and Apollo and so on. Now, you might be wondering, okay, so far we have seen a system called conditional intelligent learning or behavioral cloning that basically allow us to drive in simulation. But what happens with the physical world? What happens with the real world? How can we bring those policies into the real world? So I'm gonna be talking now about some of my own work that we did here at Intel in collaboration with Berkeley. So it's called Towards Bridging the Reality Gap for Urban Driving. It's trying to basically answer this question. So we know that there are certain strategies that work well for training agents in simulation, and those agents are able to produce very sophisticated behaviors. But can we do the same thing for the real world? Can we actually start with a simulator, train the model of the simulator, and then somehow make it work in the real world? Okay, so some of the methods that we have mentioned before present a few shortcomings. So, for example, they don't work directly in the real world. Or if they do work in the real world, the data acquisition process is very tedious. It's hard to make them converge to the right solution. It's hard to make them generalize to new environments. It's just too complicated from a data perspective. Our target for this project was simple, was to use a simulator to end up being able to drive in the real world. So we wanted to use a simulator just to cover dangerous scenarios and corner cases in a simple way. So basically, we wanted to avoid troubles with situations where you are about to crash and you need a very expert safety driver. We wanted to play it safe. We wanted to also take advantage of the safety of a simulator to expose the vehicle to more, dangerous situations in a more like an active fuzzy. And finally, we wanted to see if we could transfer those skills. So in theory, simulations should give us the benefit of presenting the vehicle with these corner cases more frequently. So we could basically cherry pick, ignore all the boring data and focus on the interesting cases. And the imitation learning approach would allow us to basically not to put too much attention into crafting a ton of modules for perception, planning, and so on, but just focus on the task of driving. This is the platform that we use for the experiments. So Lincoln MKC from 2017, equipped with a set of 3 cameras, a Velodyne LiDAR, differential GPS, a few radars, IMU, an Intel i7 processor, and 2 GPUs. For software, we use ROS, our message passing platform. So for the experiments, actually, we didn't end up using the LiDAR and radar. So we focused mostly on GPS and cameras. So we have a specific camera configuration where 3 cameras are used across a baseline of 1.5 meters. So cameras are distributed, separated like 50 centimeters from each other. We have the middle camera pointed to the center, tilted down a little bit. The left camera at minus 45 degrees, it's basically pointed to the left, and the right camera pointed 45 degrees to the right. So the idea was to try to cover the surrounding of the cars to cope with things that are happening around you. For example, a pedestrian trying to cross, intersections, and so on. Each of these cameras has a field of view of around 100 degrees. And this is what the setup looks in practice. This is what you see. Okay, now the method is a bit different than before. The idea to minimize the gap between the simulation and the real world is as follows. Instead of ingesting images directly, we introduce an abstraction layer. That abstraction layer is the perception stack. So the perception stack is going to be used to ingest the 3 images and create a high-level representation of the scene based on semantic segmentation, the activation of an object detector, and depth. Instead of training this module in simulation, what we're going to do is to use well-known data sets for perception to pre-train these models. And this block is going to be common for both the simulator and the real world. So this is going to basically create this abstraction, like the module is not going to know much about the real world, or the simulator is going to know about the dataset that we're used for training, and it's going to produce always similar activations for both domains. And this is important here. In order for this to work, the type of activations that the module produces needs to be sort of in the same range. So this is something that we have actually to verify, and we did, and it is happening. Then the output of this perception stack will be the input for the policy, for the driving policy. So this is the information that the driving policy is going to see. Now, this is very different from the modular approach. The modular approach will take like the perception stack using the semantic segmentation, the object detections, and the depth, and it will try to somehow use a set of rules to create a 3D representation of the world that will be provided to the planner. But if something goes wrong, for example, if one of the detections is wrong or the ground segmentation is wrong, the final representation will also be dramatically grown. In our case, it's different. In our case, we're using this as sort of input activations to the driving policy. They don't need to be right. We're assuming that actually they're going to be noisy. We're assuming that they're going to be faulty quite often. And the actual mission of the driving policy is to learn to tolerate errors and problems with that input representation. Finally, the driving policy is going to produce an output in what we call waypoint space. So instead of trying directly to produce a set of affordances or to produce control commands, we're going to basically produce a plan, an output plan. Like, this is where I plan to be in the next 0.2 seconds. This is going to be my position and my speed in the next 0.2 seconds. This is going to be my position and my speed in 0.5 seconds, and in 1 second, and in 1.5 seconds, and so on. So a description of the trajectory of the vehicle, where the vehicle should be. Then that is ingested by a controller. And based on that, the controller has to produce the steering and control commands. This is done on purpose so that if there is any difference between the vehicle kinematics and the vehicle dynamics of the platform in the simulator and the platform in the real world, we can quickly adapt just the controller. We can just quickly fine-tune the controller to work well in the real world without having to change the architecture. So this approach is done to prevent or to solve that problem. At the lower level, this is what it looks like. So we have 3 perception stacks, basically one to process each of the input images. Okay, here we apply semantic segmentation, object detection, and so on. And then we collect and aggregate all the activations in a large tensor. And that tensor is the input to the policy network. But it's very important to highlight that these aggregate activations don't come alone. They're very important additional information. One is the measurement. So we also monitor our speed coming from the speedometer. And what we call an egocentric map. And I'm gonna be talking about the egocentric map in a few slides, but this is a very critical component. So all this information comes together to the policy network. As we have seen in previous approaches, it computes a feature vector that then it's ingested by the different command branches. So follow, left, right, and straight, that are specialized on different action spaces. And they will end up making the low-level plan. So basically, making the decision, and in this case, the output space, as I mentioned before, is just like a trajectory that will be ingested by a controller, like a PID, to end up producing the steering control and the throttle control. So I think we don't really need to go into details for this, unless you're interested. I can answer some questions about this later. But a key element, as I mentioned before, was the egocentric map. So the reality with this approach is that sometimes the navigation space is very ambiguous. Like, you don't really know. It's hard to understand from a set of images what's the actual layout of the road. And if someone is asking you to make a left, where is the left? So we saw that the system was struggling a lot in some configurations. We tried to see if we could simplify and reduce this problem by somehow providing a very simple representation of the layout of the road. Like, and this is what we call the egocentric map. The egocentric map is basically a simplistic map of the road. So it's just a black and white image where road is white or active, and black is empty or this is not road, don't go there. And basically, we centered the map around the vehicle. So the vehicle is the red point that you see there. And we also provide the orientation for the map. So this is a small simplified oriented map. It's something that you could get from Google Maps or from any type of map. So in the end, getting this information is relatively straightforward. So you can go to OpenStreetMap. You could query for this information in real time. And surprisingly, even though this representation is very simplistic, it was good enough to remove all the ambiguities that the AI was finding in the scene. So basically now, if you're asking the vehicle to make a left, the vehicle knew exactly where that left was. And we saw a big improvement in performance after adding this piece of information. So yeah, this is just simple explanation of how to do this kind of egocentric map. So basically simple, you just have to orientate the map looking forward from the perspective of the vehicle. And that's the trick. Regarding the perception stack, the visual abstraction that we introduced, this is what it looks like. So here you have some activations for the detector. In this case, there's a traffic light that is kind of hard to see from far away, but the detector is able to catch it. Then you have a semantic segmentation network trying to segment a set of 9 classes. So for road, lane marking, other obstacles like vegetations and so on. And we also have a depth estimation network that's trying to predict the depth, the distance of the camera to different objects from a monocular camera without using stereopsis. And basically, we put all of this together, the different channels of the different activations of these modules, and we combine it into a mega tensor that is passed to the policy. This is the waypoint representation that I was mentioning before. It's basically a set of points on top of the road, predicting a few seconds ahead of you. This is a very simple way of describing a plan. And this is what is produced as an output of the neural network to be consumed by the controller. In our case, we also put some attention into improving the robustness of the network to different type of noise. So through very heavy data augmentation during the training process. So we injected a lot of noise to the different activations. So we injected noise to the semantic segmentation maps, to the detection activations, depth, etc. We modify the lane markers to make sure that the network was resilient to the lack of lane markers. We did a lot of modality dropout. For example, what happened if we totally shut down the center image or the left image or the right image, or we shut down the activation from the semantic segmentation or the activation from the detector. So basically, we really try to make the policy robust to different failures that we'll probably find in the real world. This is how a typical training clip looks like. So we are also injecting noise in the control so that the vehicle has to recover from that noise. So this is the same trick that Felipe Godevilla used in his original paper of conditional limitation learning. And it worked also well for us. And these are driving results in simulation. Here you can see different activations, the precision stack. And I think you get the idea. Of course, does it work in the real world? So this is the platform. This is Richmond here in California. Uh, and we started doing different tests, making sure that the system could work for different traffic situations, like for example, stopping at the stop, making the left turn, not getting outside of the lane, not crossing with other vehicles, stopping in the presence of other vehicles, etc. You see that this track that we're using is very sort of rural environment like. So what kind of lessons did we learn from this project, and what are the current limitations? So I think one of the important lessons that we learned is like the approach that we use didn't have any sort of temporal reasoning. And at some point when we started testing with complex traffic situations, for example, when you have to yield and remember that you are actually yielding to someone, uh, you kind of need to time it out. You need to remember, you need to have a memory saying, oh, I was in the middle of these. So right now the system that we created was still purely reactive, like experiencing every second of, as if it was just starting from scratch. Um, Having some sort of temporal reasoning would be very beneficial for the approach in order to be able to deal with more advanced situations, like as I mentioned, these deals or waiting at the traffic light, or like when you are waiting for a vehicle that is stopped in the middle of the road, you wait for a period of time until you realize something is wrong, and then you decide to overtake. So these kind of behaviors require temporal reasoning, which our agent didn't have because we didn't have the time to include it. Then we presented the agent with certain type of situations, but even in simulation, you need to select and synthesize the amount or the type of situations and corner cases you're going to be showing, demonstrating. Um, we we thought that it might be very beneficial for the pros to actually see many more. So basically to have a really large system, throwing new situations, training 24/7 until you convert to new behaviors. For this research project, we tried to keep it bounded and simple. So we selected a set of situations that we wanted to address. Um, there were simpler situations dealing with other vehicles and pedestrians and make sure that we didn't hit anything. But more complex situations will require more demonstrations. So basically select us in the simulator and collect data. Um, Overall, I think there are more elements that we can incorporate from the modular philosophy. So different representations that we can probably bring, more constraints to the policy, and ideally, we would like to get the best of both worlds, the modular and the data-driven philosophy put together to try to come up with better solutions. Um, this is actually the end of my presentation. I hope that you like it. I actually hope that you have fun and enjoy this story. And if you have any questions, I'm here for you.
Oh, hi, Herman. Hey, can you hear me okay?
Yes, I can hear you.
Okay, great. So I put 2 questions in the chat, and I asked our participants to also ask questions if they want to, put it in the chat so you can read it. Are you able to read my questions? If you want, I can read them for you.
Yeah, I can read your question, but if you want to read it for me, that's
Yes,
also fine.
sounds great. Yes. So I have 2 questions. My first question is, what is the main advantages and disadvantages of using simulation to train and validate real autonomous systems?
Then that's a very good question. So overall, a simulation gives you the space to go wild and test things that in practice in the real world will be very dangerous to test. And basically push the limits of your agent and really find all those nasty corner cases. Now, there's no a magic button today that actually produces those situations from scratch. You need a seed. You need something that has to be already predefined. And that could be a procedural engine that is going to create those situations based on grammars, where you define certain constraints of your domain. For example, the number of elements that are participating in the environment, the speeds of those elements, and then you just let it run to find those situations. If you want something more specific, you have to kind of like design it by hand. It's still probably easier and safer to design it by hand in simulation than to actually go to the real world to try to observe it. So and run it, even if you actually have to first design it in a simulator. Finding that situation in the real world might be tricky. Trying to trigger that situation by yourself might be actually dangerous. So yeah, these are the pros and cons from my perspective.
Fantastic. Excellent, excellent, very helpful. And my second question, for which tasks do simulation and synthetic environments work as expected for the training of AI systems? And also, which tasks are lagging behind? And could you please explain to us why?
Yeah, absolutely. So that's also a very interesting question. So it's true that simulation or synthetic environments overall have not been as successful for all tasks. So actually, I would say that for planning and control, for policy learning, simulation is doing very well. Simulation is an amazing tool, and you can really learn most of your policies in a simulator, and then you can transport them to the real world. Now, if you try to do a similar thing, if you try to learn something like a perception task fully in simulation, like semantic segmentation or object detection, and you try to transport that model into the real world, you're going to face what is called the domain gap. So basically, the type of statistic, the type of signal that you see in the simulator and the signal that you see in the real world don't match. Neural networks for this kind of problems, for perception problems, really suffer a lot from this domain gap. So let's say that for those tasks, we're still not there yet.